Hello, we've been talking about challenges in phase modulated sensors, and we looked at various different challenges, and we've been also looking at how to possibly overcome them. And towards the end of the last lecture, we were talking about these specific challenge of phase fluctuations due to environmental perturbations. And one way we could potentially overcome that is by using a phase generated carrier technique, right? But even when we were talking about phase generated carrier technique, we were actually looking at this paper by Dandridge et al. And we realized that the minimum detectable limit as far as the phase is concerned is going to be determined by this specific factor here, which is the uncertainty in the frequency of your light source itself, right. So, that uncertainty is essentially going to be the fundamental limitation as far as phase modulated sensors are concerned. So, let us go ahead and try to examine that in a little more detail in today's lecture. Right. So, we are talking about phase noise from optical sources . Right. And the fundamental question is why does any change in frequency or any uncertainty in frequency, why does it show up as an uncertainty in phase? How does frequency uncertainty produce phase uncertainty, right? So, how do we do that? Of course, we do understand that when we talk about frequency, like it's a monochromatic source, then you have a very definite phase for the wave that you're picking up. But if you are looking at polychromatic sources, then the phase is uncertain. So, essentially that polychromatic source is what we are actually talking about as frequency uncertainty. But anyway, if you look mathematically, what we find is the field corresponding to the optical source can be written as E naught, that's the magnitude of the field, multiplied by e power j omega naught t plus phi, where omega naught corresponds to the angular frequency, the central angular frequency of your light source, right. So, because of the fact that both of these terms appear in the phase of your optical source, even if you have an uncertainty in terms of delta nu, you have an uncertainty in terms of phase of your light source. Of course, it could be vice versa also. Any uncertainty in the phase of your light source can potentially give rise to uncertainty in the frequency, or it could appear as an uncertainty in terms of the frequency of your light source. Okay. So, if we want to actually understand this a little better, let's just take two examples. Let's actually examine the optical spectrum of a light source. Okay. And let's take the example of one light source where with respect to frequency, the optical spectrum looks something like this. Okay, it's quite broadband. So, we're talking about the optical power as a function of frequency. It's spread over a wide range of frequencies, and in this case what we are talking about is high level of frequency uncertainty, right, because the frequency can be of the optical source at any particular instant. If you take a photon, the photon can actually have any of these frequencies. So, it's a fairly high level of frequency uncertainty, and this is the characteristic of what we call as a low temporal coherence, a source with very low temporal coherence, right. Now, the same thing we can say, okay, instead of actually having your power over so many frequencies, which is possibly the characteristic of multiple longitudinal mode laser, you can say, okay, I find a way to make a single longitudinal mode laser. So, if you make a single longitudinal mode laser, then of course, you can expect that the line width is fairly narrow. So, you basically have low frequency uncertainty, and that is because you have very high temporal coherence of the source. Okay. So, you say, that's one way of making sure that my phase uncertainty is relatively low, and through that I can possibly reduce the minimum detectable limit, or I can in other words pick up phase changes that are really small. Let's say it's in the order of 10 power -7, 10 power -8 radians. Okay, so that would be quite desirable, but there is a fundamental limitation in terms of what is the lowest line width that you can achieve, what is the lowest phase uncertainty that you can achieve. And that to understand that, you have to go back to lasers, laser theory, right. So, you basically say, what is a laser? Laser is light amplification by stimulated emission of radiation, right. It's a laser is actually an acronym. So, what we are relying on is stimulated emission. So, how do you produce stimulated emission? Well, you would say that, okay, I have two energy levels, higher energy level and lower energy level. I have an inversion, meaning you have a large number of those atoms in the gain medium at the higher energy level compared to the lower energy level. Then if you have say a photon coming by with the right difference in the energy levels, with the photon energy having the right difference, then you can stimulate this transition, right. So, I can simply represent this. Let's say we are considering a 3-level atomic system. So, we are talking about pumping from your ground state to a higher energy level, and then you may have some non-radiative relaxation to another energy level, and from there you can basically say you are building up your inversion such that N2 is a significantly large number compared to N1. Then in that sort of a scenario, if you have a incoming photon with let us say h nu, maybe I will use the same color, where h nu corresponds to this energy difference, then it can actually stimulate and give you a clone of the incoming photon, which has h nu as your energy, and then so you have two photons with h nu. But there is always this possibility that you could have a spontaneously emitted photon also. So, this is basically what is called spontaneous emission, right. So, you could have a spontaneous emission event also whenever you have a large inversion and you are not utilizing the inversion with enough number of photons that are coming in to do this stimulated emission. So, this is what we desire, stimulated emission, but an undesirable byproduct of that is spontaneous emission. So, when we look at the spectrum, the spontaneous emission can be over a fairly large spectrum, right. And of course, you could find a way to filter that and restrict it to the line width of interest and all that, but nevertheless the point is that you are going to have spontaneous emission as an inevitable byproduct of any laser. Okay. So, let us examine this a little more closely and then let us see if we can what is the effect of having this spontaneously emitted photon. The key point as far as spontaneous emission is concerned, this is actually not only is producing light over a wide range of frequency. So, the frequency of the photon is uncertain. But the key point is that not only the frequency, but also the phase is uncertain, because you cannot tell that it is not timed. It is not like, okay, at this time you have exactly this many spontaneously emitted photons coming out, right. So, it's actually fairly random in nature, and that is actually a significant problem as far as phase modulated sensors are concerned. So, let us go into a little more detail about some of these things. Okay. So, to understand this, let us go back to our phasor picture. So, you are in a phasor picture, you are plotting things in the complex plane. So, the real part versus the imaginary part of the optical field, right. So, of course, what we are looking for is this phasor which corresponds to your laser, but what we are also saying is there is actually a undesirable spontaneously emitted photon which has this angle, the phase angle with respect to the stimulated emitted photon, that is arbitrarily showing up, right. So, it's basically that angle could be anywhere between 0 to 2 pi, right. So, it could be this direction, it could be this direction and so on. But what that means is your actual emission, okay, has got a certain uncertainty. The phase of the actually emitted photon has got an uncertainty, and that uncertainty, let us call this delta theta, right. The key point is this can be anywhere between 0 to pi. That means the uncertainty in the phase can be it could be, the phasor could be fluctuating around some mean position. Okay, the mean position would be determined by the stimulated emitted photon, right. So, that is the kind of scenario that we are looking at. So, let us go ahead and try to quantify what is happening over here. So, we know that so we are considering a single longitudinal mode, it is called a SLM laser. So, so that actually reduces the uncertainty as far as the phase is concerned, but even within the single longitudinal mode laser, now we are considering a spontaneously emitted photon. So, when you consider the laser intensity, we know that is corresponding to the square of the magnitude of the electric field, and this is actually a quantity that is proportional to the mean number of photons, right. So, it's proportional to the mean number of photons. That means, more number of photons, more will be the fields, the total field corresponding to that, the more will be the intensity. So, in other words, when we talk about E naught here, the magnitude of E naught, it's proportional to root of that mean number of photons, right. So, now when we consider for one spontaneously emitted photon, right, what we are trying to quantify is this delta theta. So, what is the change in the or the variation in the phase angle, and I should say that delta theta is not constant with respect to time, it is a varying component with respect to time. So, if you try to quantify delta theta, that is going to be equal to 1 over root of n cos theta, right. So, because if you have more number of photons, that is essentially stimulated emission photons, you are going to have less of this effect of this delta theta, right, that change in the fluctuation in the phase, and it has a cos theta term. That is essentially, like when we talk about beating of two fields, we have a cos of delta phi term, where delta phi here is the theta, that is the phase angle between the spontaneously emitted photon and the stimulated emitted photon. And this theta is actually a random variable, right, that is uniformly distributed, okay, over 0 to 2 pi radians. Okay. So, that is actually a uniform, that random variable is uniformly distributed over this values of 0 to 2 pi. So, so that is for a single spontaneously emitted photon. But if you consider let us say n number of spontaneously emitted photons. So, for n number of spontaneously emitted photons, what do we expect? Now, when we talk about n photons, each of those is an independent event, it is an independent random event. So, when you have independent random events happening, when you look at the combined picture of that, then it's essentially the variance of the combined event is going to be equal to the addition of the variances, the sum of variances of each of those individual events. Okay. So, if you are talking about the variance, that is delta t square for n spontaneously emitted photons. So, that is going to be equal to n times the variance corresponding to n equal to 1. Okay. And this we have already defined. So, this is basically this variance. So, what we looked at here is actually the RMS value, but if you look at the variance, that will correspond to 1 over n bar cos square of theta, and that is actually average of all those values corresponding to theta. Now, of course, if you do cos square theta and you do a average over all these possible values of theta from 0 to 2 pi, what do you get? You get a value of half. So, this can be written as n over 2 times n bar. Okay. So, that is actually the variance actually associated with n spontaneously emitted photons, and if that is the variance, then of course you can actually also find out the RMS value. The RMS value is just root of that variance. So, n over 2 times n bar. So, once again, what we are saying is n bar should be as large as possible, so that for a given inversion, most of the inversion is spent in actually emitting stimulated photons, and thereby you can keep your delta theta as low as possible. But of course, that is also mediated by what is that value of n that you have. Okay. So, question is how to quantify n. So, let us actually take this as one key result, but the question is how to quantify n, the number of spontaneously emitted photons, and specifically the question is how do you keep n to be a relatively small number. Okay. So, to understand that, you need to go back to laser theory and understand this process of stimulated versus spontaneous emission. And as we so let's for example consider a typical laser cavity. Let's say it's a Fabry-Perot cavity. So, where you have two plane parallel mirrors, and then you have a gain medium between them, right, sandwich between them, and so essentially you are pumping the gain medium. So, you have like we talked about previously, you are pumping the gain medium, and then you build an inversion N2 with respect to N1, and hopefully lot of your photons will go through stimulated emission, but like we said, you always have the possibility of this spontaneous emission happening as well. So, if we examine this this cavity, and we want to look at the dependence of n, so we ask the question what determines n. So, that is actually is determined by the cavity design and the cavity operation. Okay. So, what do I mean by this? What do I mean by the cavity design first? Well, I have these cavity mirrors you know that if you go for a high value of R, which means if you go for highly reflective mirrors, okay, then you have essentially what is called a high Q cavity, high finesse cavity, right. And if you have a high finesse cavity, what can you say about the photon that could be present inside this cavity? The photon is going to keep bouncing back and forth over a relatively long time. So, when we talk about the average photon lifetime, this means there is a high average photon lifetime. So, let us call this tau ph. Okay. So, you have a fairly high average photon lifetime if you have a high finesse cavity with highly reflective mirrors. Okay. So, how does that impact n? If you have a large number of photon build up through feedback. So, whenever there is feedback from these mirrors, that is going to actually cause more and more of the stimulated emission. Okay. Or in other words, if you have longer photon lifetime, that means there is less stimulated emission. So, you can write an expression for the stimulated emission, which actually depends on this. It's got an inverse dependence with respect to the photon lifetime, right? Because larger photon lifetime corresponds to high finesse cavity, in which more of stimulated emission is happening. So, so you have lesser probability of spontaneously emitted photons. But it also depends on the inversion that you have, and specifically the inversion such that so when we talk about inversion, we are talking about a lot of these atoms sitting in the higher energy level compared to the lower energy level. We are also talking about the utilization of the inversion. That utilization of the inversion is something that can be represented by this factor mu, where mu is given by n2 over n2 minus n1, right. So, n2 is actually the number of atoms in the excited level with respect to the total inversion, right. If you have a large number of atoms that are at the excited level with respect to the inversion, and essentially you do not have as many stimulated as many photons that can stimulate this this transition, then that is going to give rise to more of spontaneous emission. So, it is proportional to mu, right. So, this is mu into mu divided by tau photon multiplied by your observation time. So, let us say the observation time window is given by t. So, what we are talking about, this is the observation time. So, in a practical sense, what determines the observation time, that is dependent on the receiver bandwidth. Right. So, the receiver bandwidth can be written as 1 over 2 times t, right. T corresponds to the observation time. So, over that observation time, you might actually have n spontaneously emitted photons, and where n is determined by this inversion as well as your photon lifetime, right, inside the cavity. So, now I can substitute this over here. We have quantified n. So, I can just say your delta theta of t now corresponds to 1 over 2 times n, right, where n is the number of mean number of photons, and multiplied by mu over tau photon multiplied by t. Okay. So, what we are saying is, let's go from this side. So, larger, if you have low bandwidth receivers, you are integrating all these events over a longer time, and that means there is clearly more possibility of spontaneous emission, and more spontaneous emission means more fluctuation in terms of the phase, more uncertainty in the phase. It's inversely dependent on the root of the tau photon. Well, why do we talk about root? Because the variance is inversely proportional, but when we are talking about the RMS value, there is a root that comes into the picture. But it's inverse proportional to tau photon, which means that if you want to reduce delta theta, the phase uncertainty, you have a larger photon lifetime, which means you go for a higher finesse cavity. And then it's also dependent on mu, which corresponds to how effectively use up the inversion. If N2 is if all your atoms are at the excited state, so mu can actually be as low as 1, because n1 becomes 0, then you have mu equals to 1. So that is one way of well, in that case you may not have as many photons stimulating this transition. So that's actually the so that can give rise to a lot of well, if you, okay, let's just rephrase that. If N2, if the inversion, the highest value of inversion could be N2 by itself, right? So if you have more photons in the ground state, then that means N2 minus N1 is a value that's smaller than N2, and that means mu is a much larger value. And when mu is much larger, that means there is actually much more spontaneously emitted photons, and then because of that you have much more uncertainty in the phase of your optical field. Okay. So let's actually put all of this together and let's see what it means from an interferometer perspective. So let's do a quick recap on what we've been talking about. So we've been looking at how to extract this phase changes phi of t, and of course we realize that we're going to have to do this differentiate and cross multiply scheme to extract phi of t. Let's just talk about how to optimize this phi of t. Okay. So to optimize this, we need to take care of all these factors J1, J2, B, G and H and all of that. So let's just look into all of this one by one. Let's first look at the Bessel components. So what do these Bessel components mean? Well, you can draw this Bessel function J of phi c as a function of phi c. So if you draw the different Bessel functions, so let's say you start with J naught. J naught is actually going to be an oscillatory component with the exponential decay of the envelope, and then you look at J1. J1 is going to start from 0 and then So J naught actually starts from a value of 1, whereas J1 starts from a value of 0, and then once again it's oscillatory, but it doesn't swing as much as J naught does. And then J2 is another oscillatory function, but that doesn't go up as much as J1. So it's relatively smaller in amplitude, but that's also decaying and oscillating. Now the question is, what is the optimum value of phi c that you can choose? Remember, phi c is something that is up to you, because you actually send a voltage from your signal generator to drive your PZT, and the voltage should be such a value, like you can call this Vc. So such a value that it incorporates a certain phi c through this PZT. So then the question is, what should be that phi c? Now the phi c should be such that when you have small changes in phi c, let's say it's although you give a very specific voltage to get a very specific phase point, the voltage might have some small changes, like it might go from 2.59 to 2.61, it may be fluctuating by about 0.01 radian. If there is any such changes, it should not cause a big change in the phase that you are trying to extract. So you choose a point such that if it goes less than that value, let's say it goes 2.59, J1 is increasing, J2 is decreasing. So when you are looking at the product of J1 and J2, that is constant. Okay. And similarly, if this phi c value goes up to 0.01 higher, it goes to 2.61, J2 is increasing, J1 is decreasing. Once again, the product is not going to change as much. So you look for these crossover points between J1, J2. So there is one crossover point here, another crossover point here, another crossover point here, and so on. So you can conveniently choose this crossover point, so that that will be your optimum bias point, so that any small changes in small fluctuations in phi c should not change the overall phi value that you are trying to pick up. And then it comes to optimizing the value of G and H. Okay, how do you optimize the value of G and H? Now when you think about the final power value that you are reading, this phi of t you are reading, phi of t you're typically designed for a certain range. There is a maximum phi value for which you design this sensor. Okay, let's say that maximum phi value is 1 radian. Okay, so it should be such that this final phi of t that you are getting is actually a voltage value. Okay, so that voltage should fill your ADC. So if your ADC is, say, ADC is 1 volt, then that 1 volt should correspond to 1 radian, if 1 radian is the maximum phase that you are trying to pick up. Okay, so you need to fill your ADC. So to fill your ADC, you can use, you can actually change the value of G and H. What does G and H represent? G represents the strength of the signal that's coming here. H represents the strength of the signal that's coming here, right? So you can actually change those voltages so that you can increase the signal that you are final signal that you are getting, such that it fills the ADC, right? So that's how you go about choosing G and H. And finally, you want to choose B carefully. So let's actually see what B represents. To see that, you need to go back and look at your the original where it all started. We said we are looking at this beat function. The strength of that beat is what we are calling as B. right. So, that is what we used in these expressions. This B is representing this value. And when you look at this closely, it consists of the degree of coherence, which you of course try to increase as much as possible. You try to choose a laser which is relatively narrow line width. So, you can get a fairly high degree of coherence, close to 1 if possible. And then you have the relative values of I1 and I2. So, how do you choose I1 and I2? Well, to start with, you in an interferometer, to get maximum contrast, you try to get I1 to be matching I2. Okay. So, you can adjust the intensities in the two arms by adjusting the losses in the two arms. So, you can balance I1 and I2. Okay. So, that is one thing we do, and overall it is controlled by the intensity from the laser. So, you can actually this if you call it I0, you can adjust I0 so that you can adjust I1 and I2 as well. But what should those values be? Well, we understand that in our receiver you have what is called short noise. Okay. So, what is short noise due to? It is because of the random arrival time of photons at the receiver, and that actually scales with the short noise variance scales with the input power or the input intensity of light that's incident on the detector. Okay. So, you need to reduce the intensity I1 and I2 such that you can reduce the short noise component. But if you reduce this to too small a value, let us say you go down to nanowatts of power, okay, in that case you need to actually boost up your signal by having a large gain for your receiver, and in that case you have a thermal noise component that comes into the picture. So, you need to essentially adjust I1 and I2 so that you can balance this short noise and thermal noise so that you can achieve as high a signal to noise ratio as possible. Okay. And by adjusting I1 and I2, you are adjusting B, and through that you are essentially making sure you get a relatively clean signal. Okay. So, you can extract this phi of t in a reliable manner. Okay. Having said that, we do have to be careful about this phi of t as we defined a little earlier. It corresponds to phi s cos omega st. This is the signal that we want to extract, but there is still noise incorporated in that. We are reducing the noise as much as possible through this lock-in detection and low pass filtering. That is something that I did not explicitly mention previously. When you do this beating, you also need to incorporate this low pass filter before you extract this 1 and 2. So, by low pass filtering to essentially include the essential components, like if you are trying to pick up something at 100 hertz, then you do a low pass filter around that, so that you are not actually accumulating a lot of noise from higher frequencies. Okay. So, you need to use this low pass filtering judiciously. On the other hand, if you know that your acoustic signal that's incident on this, right? If the acoustic signal that's incident on this hydrophone, if you know it is going to be at 100 hertz, let's say, then instead of a low pass filter, you can actually use a band pass filter. Okay, and then just pick up that 100 hertz component, or even better, you can beat it instead of FC, you can beat it with FC plus 100 hertz or something like that, and then you can extract the specific component corresponding to and 2FC will correspond to 2FC plus this 100 hertz or 200 hertz, those components, and then you can extract the specific frequencies of interest for us. Okay. So those are some of the modifications you can do to reduce the noise further, but that is essentially what this phase generated carrier method is all about. Of course, I want to acknowledge that most of this material is coming from this 1982 paper, that is in Journal of Quantum Electronics in 1982 is when this scheme was first proposed, and by Dandridge et al. And they were looking at these picking up phase values in the presence of low frequency random temperature and pressure fluctuations, right. So that is what they want to deal with, and they are targeting 10 radians to 10 power minus 6 radian type of range. And to achieve that, they are essentially proposing this phase generated carrier technique, which involves using this piezoelectric phase modulators, right. And this is all the math that we went through previously. So all that comes from this this paper here. And once we have this cos phi t sin phi t terms, then you do this cross differentiate and cross multiply scheme. First you do the beating and you get the FC and 2FC components, and then you do the cross differentiate step, and then the cross multiply step, and then your subtraction, and then finally you integrate to get the phi of t term. And here are some sample waveforms that they acquired experimentally at that time. This is actually for a condition where your FC component is dominant compared to this 2FC component. So, this is closer to quadrature, and this is actually a case where your 2FC and 0 the DC components are dominant compared to the FC component. So, this corresponds to a case where phi is closer to 0, right. So, of course, they talk about this beating at the FC and 2FC to get those beat components, and then they talk about how to do this differentiate and cross multiply scheme to extract phi of t. And what they mentioned there is they are able to get to about 10 power minus 6 radians to about 1 radian in their work, which is of course has been, this was almost 40 years ago. So, it has been improved since then, but they also make another important point, which is what is the minimum detectable limit as far as this phase generated carrier technique is concerned. What is it really limited by? What they observe is limited by the fluctuation of the emission frequency of the source. If you have a single frequency source, then you have a single phase, a very definite phase associated with it. But if your source is actually having multiple frequencies, then the phase actually does not become deterministic. There is some uncertainty in the phase itself, and that uncertainty is going to constitute the minimum detectable limit as far as the phase detection is concerned. So, not so surprisingly, that detectable limit in terms of phase is proportional to delta nu, where delta nu correspond to the spread in the frequencies of your source. So, we will look into this aspect a little more detail possibly in the next lecture. Okay. So, that is what we have, a phase generated carrier technique to pick up phase changes in the presence of environmentally induced phase noise.